The third part of our lecture on minerals and rocks will discuss minerals as gems and minerals in rocks. So gems are minerals that have been polished and cut and are particularly beautiful, so much that they have monetary value. A gemstone is a mineral that will become a gem if it is cut and polished. For example, corundum is a type of mineral that's called a ruby when it's red and sapphire when it's blue. So ruby and sapphire really have the same bulk chemical composition and structure. They're all from the same mineral, it's just they have different small impurities that change their color. Facets are smooth faces on gems that are created when gem cutters grind and polish specimens. It's important to note that they are not crystal faces or cleavage planes. These are completely made up by humans to make them reflect light very well and refract light very well and make them shiny and beautiful. So that's what a picture on the bottom left shows. And they do this using this grinding machine and polishing machine shown on the right side of your screen. Secondly, we want to discuss where diamonds come from. Diamonds are the hardest mineral. They're 10 on the most hardness scale we talked about earlier, and they form at great depth, more than 100 kilometers beneath Earth's surface from the element carbon. They do not form from coal, but they are made up of pure carbon, just like coal is. It's just that in this case they've been subjected to very high temperatures and pressures that changes the atomic structure and thus the crystal structure of the carbon atoms in forming the mineral. So in the case of diamonds, diamond-rich magma comes to the surface and forms a rock called kimberlite, and that's where the diamond minerals can be found. So on the middle picture we have a mine, maybe in Canada or somewhere, where they've got kimberlite exposed near the surface that they're digging into to find diamonds. And in the inset photo is a picture of a kimberlite with a diamond inclusion. So now that we've discussed minerals, we want to actually find out what is a rock. Well, a rock is defined as something being coherent or held together by a solid mass, naturally occurring, and an aggregate of mineral grains and or mineraloids. So all of these make up the definition of a rock. Bedrock is rock at or near Earth's surface that hasn't been eroded or transported. It is still attached to the crust below, and this is known as in place or in situ. So the rocks below on the two pictures to the bottom right are both in situ rocks. If a boulder had fallen off the mountain or tumbled into the river, these would not be in situ anymore. These would not be bedrock. These photos are also pictures of outcrops. So outcrops are surface exposures of bedrocks on land. So bedrock can be beneath the surface. If you drill 10 feet within the surface beneath Gainesville, for example, then you may hit bedrock, but that is not outcrop because it's not exposed at the surface. So there are three main different rock types, and they are defined through their origin or how they formed. Igneous rocks formed when molten or liquid rock, also known as magma or lava, solidifies at or below Earth's surface. Sedimentary rocks form when small grains are cemented together or by the precipitation of mineral crystals at Earth's surface. And metamorphic rocks form when pre-existing rocks change, but don't completely remelt due to increased heat and pressure, mostly within Earth's crust. This often produces new minerals. Igneous rocks were the first types of rocks to form on Earth, and after that, sedimentary rocks and metamorphic rocks formed. Another way to describe rocks is whether they're crystalline or clastic. Crystalline rocks have grains that grew to interlock with one another, so they grew together in the same environment or at more or less over the same time period. Clastic rocks have grains that are held together by cement, where both grains and cement precipitated out of water, so they fell through water or came out of water. Igneous and metamorphic rocks are crystalline, whereas sedimentary rocks can be both crystalline and clastic. So this depends on whether a cement was precipitated interstitially between grains or whether precipitated grains grew together interlocking with one another. It should be said that this isn't a super common way to look at the rocks. It's much better to look at them first, whether they are igneous, sedimentary, or metamorphic through their mode of formation or their origin, and then determine what they look like in terms of their crystals. The rock cycle shows how rocks get recycled through geological processes in Earth's crust and mantle. So the three different main types of rocks on Earth, igneous, sedimentary, and metamorphic, change over geologic time. As igneous rocks form from lavas and magmas, they solidify as they cool and become rocks at or near Earth's surface. As these rocks get weathered, eroded, transported, and deposited, then eventually lithified and buried, they become sedimentary rocks. Sedimentary rocks and igneous rocks can be buried to even greater depths and heated and undergo metamorphic changes to become metamorphic rocks. And if metamorphic rocks or sedimentary rocks are completely melted, then they will become igneous rocks again over a period of geologic time. So as you can see, the rock cycle doesn't just go in one direction. There are many directions that the rocks can take depending on the length of time and the geologic conditions that they are subject to over that period. Now that we have defined the different types of rocks, how do we identify them? Well, physical characteristics can be identified in the field or at the outcrop or in the lab using microscopes. In the field, there's three main ways that we use to distinguish rock types, and they are texture, which in the case of a geologist means grain size and shape. It does not mean roughness or smoothness of grains. There's composition, which means the mineralogical composition or the chemical composition if you're in the lab. And then there's layering. There's different types of layering in igneous, sedimentary, and metamorphic rocks, and we'll discuss each type of layering for each of them as we discuss the rocks in each chapter. We have texture, which is grain size and shape. Dimensions can be visible to the naked eye and described in terms of length or diameter, for example, in millimeters, or grains can be so small that they can't be seen without a microscope. If we're doing a qualitative description, we would describe large grains as coarse and small grains as fine, but it's always better to do a quantitative description because qualitative descriptions are subjective. Grain shapes can be equant with similar dimensions in all directions or inequant where dimensions vary with direction. So in the case of the rocks below, the green rock with red crystalline grains has inequant grain size because there's a variety of sizes of diameters of the grains, and they're not spherical or circular. And it also can be described as coarse because the grains can be seen. We don't have a scale here, so we don't know the actual size of the grains. The bottom on the rock on the top right figure, the red or maroon, tan, and gray rocks all have grains so fine that they are unable to be seen. So this would be described as fine-grained. Next is composition. And this is typically what minerals are the grains made of. In the field, we are able to identify minerals in rocks through the aid of a magnifying glass. But in the laboratory, we're able to use microscopes and chemical analyses to determine elemental compositions. So this is defined differently depending on where you are and what level of analysis or observation you're doing. But in the field, we look at minerals because we can see them. So on the figure on the left, we see that this green rock is made up of these green minerals, which are olivine and epidote, and the red mineral, which is garnet. This rock is called an eclogite. And on the top right figure, we are unable to tell composition because the grains are too small, although we know based on the rock type that these are made of clay minerals that have been worn down so much as to where you cannot see the grains. On the right, we've got compositional differences in each of the bands. We've got, or layers, we've got pink and white and dark gray or black minerals in different positions that can be described. Last, we have layering, which is defined as bands of different compositions or textures, or by the alignment of inequal grains. So in sedimentary rocks, this is known as bedding. We have bedded sedimentary rocks on the top left figure with the human standing on the outcrop. We can see the different horizontal layers. This is also true in the top right figure of the three hand sample rocks that are red, tan, and gray. These are also sedimentary rocks with bedding. In metamorphic rocks, layering is called foliation. This only occurs in some metamorphic rocks that have minerals that will be able to be oriented in planes, and we have foliations in the bottom left and bottom right rocks. Both of these are metamorphic. Igneous rocks sometimes have layering as well that shows the flow of the magma, but this is less important than the layering in sedimentary and metamorphic rocks in terms of determining the evolution of the rock. In the laboratory, we identify rock types through something called petrography, which petro meaning rock and graphy meaning the writing of, so the writing of rocks, if you want to look at the entomology. A thin section is a slice of rock sample glued to a piece of glass with a thickness of 0.03 millimeters. This is so thin that light can pass through it. And so we put these thin sections on our microscopes and are able to view the minerals and the relationships between the minerals in very high detail. A photomicrograph is a photo taken through the lens of the petrographic microscope. So here we have a petrographic microscope, a photomicrograph, and a thin section on the bottom right. It's important to note to connect this with the identification methods for rocks. So with this method, we can identify grain size, which is texture, grain type, which is mineralogic composition, and connections between grains, which would be something like layering.